Okay, dear students, I'm now over this course, which is MSM 111. This course, which is MSM 111. This course, which is MSM 1. Yeah, we'll be looking at lecture number 14, which talks about partial fractions. So under partial fractions, we are going to look at three components, which involves partial fractions. So under this, we are going to look at what we call rational fractions. I think we've been talking about rational fractions, rational functions since the set of the semester. From the start, the rise of the semester up to the time that we finished. So we looked at rational functions. When we are looking at functions, we also talked about them when we are looking at polynomial functions. Then under these partial fractions, we are strictly going to look at partial fractions with linear factors. We are going to look at partial fractions with repeated factors. We are also going to look at partial fractions with quadratic factors. So generally, by 13:10, so we should be done with this lecture. As such, I'm going to start now. Before we look at partial fractions, we need first to look at what are rational fractions. So let's start. Now, if you look at what is displayed here, we are going to look at rational fractions. Rational fractions comes from what we call the rational functions that we are looking at when we are dealing with polynomials. So a rational fraction in the variable x is the quotient. Now see, this is the quotient. We have px, which is a function, which is a polynomial. We also have qx, which is a polynomial of two polynomials in x. So these two polynomials are polynomials of the variable x. Now, the expression which we have displayed below, these are examples of rational fractions. So rational fractions comes from rational functions. Now, if you look at these three, these are not the only rational fractions that we know. There are a lot of them. There are a lot of them, a billion of them that you can't manage to count. So these are called rational fractions. Why are they called rational fractions? Because they are in rational form and they're in fraction form. As such, we call them the rational fractions. Now, if I add an f of x in front or whichever if I add f of x, which is equal to 3 over x plus 1, then this becomes a rational function. Those are the ones we are talking about, rational functions. We're even finding examples of rational functions or like in such scenario. Now, from the rational function definition, we also have what we call improper rational functions. An improper rational function, these are functions, we have proper and improper. So a proper fraction is one in which the degree of the numerator is less than the degree of the denominator. So if you have such kind of a fraction where the degree of the numerator is less than the degree of the denominator, then we call those proper fractions, or rather proper rational fractions. Now in this case, as you can see here, if you check in each case of this, there are about 5 rational functions which are displayed here. All these are proper rational functions. Reason being, because the highest degree of the denominator is higher than the highest degree of the numerator. Now, if the highest degree of the numerator is greater than the highest degree of the denominator, then we call them improper rational fractions. Like in this scenario, if you look at the degree of the numerator is 3. Now, if you look at the highest degree of the denominator is 2. So these are examples of improper rational fractions. Now, every time we have an improper rational fraction, or rather an improper irrational fraction or an improper rational function, these such kind of rational fractions can be divided. You can divide this using long division, you can use synthetic division, whichever method that you can think of. So there are 2 ways on how we can do this. when you divide them, you can always have a quotient and a remainder. So this means it's taking us back from what we are looking at, the remainder theorem and the factor theorem. Now, so this we've seen, this improper rational function, we can divide it, and at the end of the day, we are going to produce this expression with 12x plus 12, 2x plus 12 being the quotient, and the remainder being 32x minus 33. So every improper rational function, you can write it in this form. Now, what you're going to look at now are what we call partial fractions. So you need to pay much attention to what I'm explaining. What is a partial fraction? So whenever we are given a rational fraction, remember we looked at rational fractions. So whenever you are given a rational fraction, for example, this fraction which is f of x, so this fraction which is given as f of x, which is equal to px over qx, remember px is a polynomial, qx is a polynomial. We don't know whether it can either be a constant, they can all be constant polynomials, or one of them is a constant polynomial, another one is a linear or quadratic polynomial, whichever kind of a polynomial. Now, this means this rational function can also be written, this rational function you've seen, with px being the denominator and qx being the numerator, with px being the denominator and qx being the denominator. So basically, px is the numerator, qx is the denominator. You can write it as a sum of other fractions. Now, this expression is a fraction, is a rational function which is in fraction form. Now, this rational function, you can also write it as a sum of other fractions. So now, that sum, those fractions that you have combined to form the px over qx, those are the ones we call partial fractions. So these fractions that you are writing as being the sum of px over qx, those fractions are the ones that we call the partial fractions. These partial fractions, these fractions that you have written the rational function p fx, which is equal to px over qx. If you look at them, we are going to discover that the denominators are of lower degree than the numerators. So in short, the numerators will always be of lower degree than the denominators. So these fractions, these partial fractions, will always have their numerators of lower degree than the denominators. Now, how many types of partial fractions that you have? Now, we have about 3. So there are basically 3 types of partial fractions, namely those partial fractions with denominator containing linear factors, those partial fractions with denominator having the repeated linear factors, and also those having the quadratic factors. So we are going in each case. So in each case, I'm going to look at each component one by one. So we are going to look at each section of this component one by one. So I will look at each part, 2 examples on each component. Like we are going to look at partial fractions involving linear factors. We are going to look at 2 examples. We are also going to look at partial fractions involving repeated linear factors and then quadratic factors. So we are going to look at each part, each component, 2 examples, then from which we can call it the end of this session. Now, let's look at the first one. So, resolving rational functions into partial fractions. Now, this is an algorithm. This is the most important thing that you need to understand before you convert a given rational function into partial fraction. The first thing, so in order to resolve a given rational algebraic expression into partial fractions, there is one thing that you need first to note. One, the denominator must be factorizable. The denominator must be factorizable. If the denominator is non-factorizable, then you can't convert the given rational function into partial fraction. The second point that you need to take note is that the numerator must be at least 1 degree less than the denominator. The numerator must be at least 1 degree greater than the denominator. So what we're saying is for you to convert any given expression into partial fraction, the numerator must be at least 1 degree less than the denominator. And also, when the degree of the numerator is equal to or higher than the degree of the denominator, then the numerator must be divided by the denominator until the remainder is of less degree than the denominator. This is the situation here. So whenever you see that, every time you are converting a given rational function into a partial fraction, the first thing that you need to take note is that the denominator must be factorizable. The second part is that the numerator must be at least 1 degree less than the denominator. So what you are saying is the degree of the numerator must be less than the degree of the denominator. Then you can convert a given rational function into partial fractions. Now, there's another thing. Now, what happens if the degree of the numerator is equal to the degree of the denominator, or if the degree of the numerator polynomial is greater than the degree of the denominator? So in this case, what you need to do first is you divide. You can use either long division, you can use synthetic division. When you do the division, and then you need to rewrite the given expression in the form, for example, you need to write the given expression in this form, like this form that you've written here. Now, from which then, that's when I can convert that given expression into partial fractions. So now let's look at some examples. So here in this scenario, in the first, that is 2.1, we are looking at partial fractions with linear factors. So what do we mean here? So if we have a function f of x, so we are saying let f of x be a polynomial. By being a polynomial, we know what we mean when we say let x be a polynomial. Now, then the partial fraction form of the rational expression. So if you look at this rational expression has the numerator f of x, the denominator, this denominator has 3 factors, x plus 1, x plus b, x plus a, x plus b, x plus c. So this is the denominator of this rational function. Now, if you look at this rational function, the denominator has linear factors. This is x plus a. A, b, and c are numbers, are real numbers. They can be real numbers, they can be complex numbers. Now here, the real numbers, we are dealing with real numbers, not complex numbers yet, because you've not yet done complex numbers as in a topic, So as such, now, if you have such a scenario if your rational function is of this form, with denominator containing linear factors, then this is how you can write it as a rational function. So this expression, its partial fraction form is capital A divided by x plus a plus capital B divided by x plus b plus capital C divided by x plus c. Now, this is where the question is. Then now, let's go now to the next part. This one is an example of a rational function. Now the question is, let's look now how we can solve questions that involves rational functions. Now we are going to look at how we can solve questions involving rational functions. Okay, so what I'm going to do is I'm going to beam, and then we're going to see some examples that involves rational functions. So this is our example number 1. Okay, can just excuse me. Okay, so now we are going to look at how we can solve a rational function into partial fractions. So in example number 1, the kind of rational function that we have is 11 minus 3x divided by x squared plus 2x minus 3. So they are asking us to resolve this rational fraction into partial fractions. Now, let's look at this rational function. If you look at this rational function, the denominator is factorizable. The denominator, you can factorize. This is a quadratic expression that you can factorize. You can factorize it into linear factors. So the denominator is factorizable, and if you factorize this denominator, it will give us x minus 3 times x plus 3. Now, after you do that, and the numerator is of less degree than the denominator. If you look at this from the original partial fraction, if you look at the numerator, the highest degree of the numerator is 1. The highest degree of the denominator is 2. This means it's satisfying property number 2, number 1, which says that the degree of the numerator should be less than the degree of the denominator. The other thing is, it's satisfying property number 2 because the denominator is factorizable. It's not about the numerator, it's about the denominator. Is the denominator factorizable? You are going to have a situation of questions where you find the numerator is not factorizable. So this is about, is the denominator factorizable? Can you factorize the denominator? So now, let's look at this. Now, if you look at this partial fraction, 11, maybe the best thing I can do, let me just beam this so that you can see what I'm doing. So that you are able to observe what I'm solving on the board. Okay. Okay, so what we are looking at is a situation where we have a rational function. The rational function is 11 minus 3x divided by x squared plus 2x minus 3. So now this rational function, I guess everyone you are able to see what I'm writing on the board. You need please to tell me if you are able to see or you are unable to see, so that I can see what I can do. So now, okay. Okay, so I hope everyone is now able to see what I'm writing on the board. Okay, so we are going to solve this equation, this partial fraction, which says that 11 minus 3x over x squared plus 2x minus 3. Okay, others are saying they can see, so I don't know what is the problem. But are you able to see now? Okay, are you able to see now? Okay, I hope now you are able to see what I'm writing on the board. Is everyone able to see? Okay, if that's the case, then we can just use I can just use the slides, because the some they are unable to see. Okay, are you able to see now? All right, okay, then we can continue. Okay, so now what we are saying is if you look at this partial fraction, we can convert it. I mean, if you look at this rational function, we can convert it into partial fractions. So generally, this which we can also write as 11 minus 3x divided by, when you factorize this quadratic denominator, what you're going to get is x plus 1 multiplied by x minus 3. Now, it's x minus 1 then plus 3. Now, because if you look at x minus 3 and x minus 1 and x plus 3, these factors are linear factors. So these are linear factors. As such, this means this partial fraction, we can also write it as in a simple manner, where in this scenario now, what you're going to write is you can also write this partial fraction as 11 minus, so in this case, because we have this scenario, what we're having is, according to the standard that I mentioned, what you're having, this is similar to the situation where you have f of x over, we have x plus a, x plus b. So if you have such kind of a rational function, then you can write it as capital A divided by x plus a plus capital B divided by x plus b. Remember, small a and small b are already given. So now, in this case, since we have this, comparing it to this, so what you're going to get is this. So because we already have our f of x in this scenario is 11 minus 3x, and then the first, so this expression, we can write it as a divided by x minus 1 plus b divided by x plus 3. So our main goal is now to find the value of a and b. So now when you reach this stage, you are supposed to find the values of a and b. Now the question is, how can we do this? So the easier way you can handle this is like this. So if you want, the best thing, you can write this expression. When we write this expression, so what you're going to get is, then what you're going to get, we are saying the 11, which is minus 3x over x minus 1, x plus 3, this is equal to the a divided by x minus 1 plus the b divided by x plus 3. Now, we are at this stage. What should we do? So to handle such a scenario, what you can do is, because we want to find the value of a and the value of b, so what you can do is, you multiply, this is another way of doing it, you multiply both sides, or you multiply both sides, or each term on both sides by the original denominator. So by x minus 1, x plus 3. So what we are going to do is, now we are going to multiply each term in this expression here. Let's give it a start. So you multiply each term, each side or both sides, or each term on both sides by x minus 1 and times x plus 3. So now, if we do that, if we multiply each term in that scenario, so what you're going to get then is this. So if we multiply each term, or rather both sides of that expression by x minus 1 times x plus 3, what you're going to get is this. So on the right hand side, on the left hand side, we have x minus 1, then x plus 3 multiplied by 11 minus 3x divided by x minus 1, x plus 3. This is equal to, so again, we are going to multiply this same denominator. This denominator is for the original partial fraction. We also multiplied the x minus 1, x plus 3. Sorry, maybe we can, yeah. So this one multiplied by a divided by x minus 1. Then plus, again, x minus 1 times x plus 3 multiplied by b divided by x plus 3. Now, if now you look at this new expression, you see this product will cancel with that product. Also, the x minus 1 will cancel with the x minus 1 in the denominator. The x plus 3 will cancel with the x plus 3 in the denominator. So generally, what we are going to get from this is, on the left hand side, we are going to remain with 11 minus 3x, which is equal to the x plus 3 multiplied by a plus the x minus 1 multiplied by b. So now, when you reach this stage, simplifying, if we simplify, we expand the left-hand side, we expand the right-hand side, what you're going to get is ax plus 3a plus bx minus b. Now, when you collect the like terms, you know we have ax plus bx, which will give us a plus b, then x, then we also have 3a minus b. Now, I remember when we are looking at polynomials and we're also looking at quadratic equations, we looked at what we call identical polynomials. So now, in this scenario, what we are saying is, when can the left-hand side, so maybe if I can write it, so generally, from what I've written here, this is going to give us, in this case, what we have is 11 minus 3x. So we are going to have 11 minus 3x is equal to, so if I write it in this form, we are going to have 3a minus b, then plus, so we also have a plus b, then x. Now, after reaching this stage, when can these two be equal? These two can only be equal if the coefficients are the same. What do I mean by the coefficients? We are saying the constant coefficient on the left-hand side must be equal to the constant coefficient on the right-hand side. Also, the coefficient of x on the left-hand side must be equal to the coefficient of x on the right-hand side. Now, if you look at this expression, so let's start with the constant coefficient. So you equate the constant coefficient together and also the coefficients of x together. So what you're saying is, when you reach at this stage, then you say equating the constant coefficients to and the coefficients of x together. This is respectively. So I've used the word respectively, means each part. Now let's look at the right hand side. The left hand side, the constant coefficient is 11. On the left hand side, the constant coefficient is 3a minus b. Again, on the left hand side, the coefficient of x is negative 3. On the left hand side, the coefficient of x is a plus b. So basically, what we have from this is just the equation, the linear system of equations in two variables. This is a linear system of equations in two variables, which is x 3a minus b is equal to 11 and a plus b is equal to negative 3. Now, if we solve for a and b, what are we going to get then? From this equation, once we solve for a and b, what you're going to get is, so solving, this is a system of linear equations in two variables. This is a system of linear equations in two variables. So if we solve for a and b in this system, basically what you're going to get is that your a will be equal to 2 and our b is going to be equal to negative 5. So then, from this now, after you have found your a being equal to negative 2 and your b being equal to negative 5, then you need now, this means wherever there is a in the expression that we wrote, so what you're going to get now is this. Now our rational function our rational function now becomes, so our rational function which was equal to 11 minus 3x divided by x squared plus 2x minus 3. This is equal to, now remember we said that this expression was equal to a divided by x, was it plus 3? Oh no, it was minus 1, then plus b divided by x plus 3. So now this means where there is a, we are going to put a 2 divided by x minus 1, and where there is b, we are going to put a negative 5 divided by x plus 3, from which we can just have x minus 1 then minus 5 over x plus 3. So what we have done now, we have written this expression. So what we have done now, we have written this expression, which is 11 minus 3x over x squared plus 2x minus 3 as a partial fraction. So now, if you look at these two, this one and this one are the partial fractions that you're talking about. So every polynomial function can be written as a sum of fractions. Now, if you look at this fraction, these fractions are of lower degree than. Now, if you look at this fraction, look at their denominators. The denominator of the first partial fraction is x minus 1. Now, the highest degree of this denominator is lower than the highest degree of the original denominator. You can also look at the other one, which is x minus plus 3. The highest degree is 1, which is also of degree less than the degree of the original denominator. So this is the first question that I talked about, which we are supposed to do under this session. Now, we are going to look at another type of partial fractions. I said I'll give you two examples. As such, we are also going to look at another scenario in this case. Okay. Okay, so let's now look at another scenario in which we can construct also partial fractions. Now, another example is this example. So another example is this example. So the next example says convert. It's saying convert 2x squared minus 9x minus 35 into the sum of three partial fractions. So they want you, basically we are not finding the value of x, we are solving the values of a and b, not the values of x. We are just converting the given rational function into partial fractions. So let's look at I think the 2 and negative 5, when you solve that equation, what are you going to get? When we solve the equation, what are we going to get? Okay, the board is too far. Okay, so I just have to blind you from the board. I just need to concentrate again on the other parts. So let's now look at the next part. So others are saying a is equal to 7. Oh yeah. I think there is a typo. Yeah, okay, those are just typos that we can rectify. So A is equal to 7, A is equal to 4. So we have all those kind of expressions. So basically, okay, maybe what you can do is you can look at it at your own time and then you check if what we have written, maybe they are supposed to be typos in such a case, but okay, where are we? So what we had is okay, there was just some typos. Okay, now let's look at the next example. So the next example we are looking at, please, you can compute it. Then these typos I'll rectify them later. So okay, let's look at example number 7, which says convert 2x squared minus 9x minus 35 into divided by x plus 1, x minus 2, x plus 3 into the sum of three partial fractions. Now, if you look at this example has already been, so this example has already been, if you look at the denominator is already a product of three factors which are linear. So here you don't need first to factorize or do any other things, so we can just go direct. So this one now, this rational function, we can write it as a divided by x plus 1 plus b divided by x minus 2 plus c divided by x plus 3, x plus 1. Now, in this is how this given rational function can be expressed as a sum of partial fractions. Now, the aim here is that we are not aiming to find the values of x. No, we are aiming to find a, b, and c. The question is, what is the value of a, what is the value of b, and what is the value of c? This is the question that we are asking ourselves. So, by algebraic addition, so now, let's look at this. So, if, in short, what we are going to write by algebraically, I know some of you are saying, no sir, you can't do that. So this you can also use it. Now, if you look at this expression, you look at a divided by x plus 1, b divided by x minus 2, c divided by x plus 1. If you add these three algebraically, what you're going to get is, you're going to get a multiplied by x minus 2 times x plus 3, then plus b multiplied by x plus 1 times x plus 3, plus c multiplied by x plus 1 times x minus 2. Now, if you look at these two expressions on the right hand side and on the left hand side, you check that these expressions have the same denominators. So if they have the same denominators, the only possibility you can have such is when the numerators are the same. For these two to be equal and the denominators are the same, since the denominators are the same, for they to be equal, which means the numerators must also be the same. So what we're saying is the 2x squared minus 9x minus 35, this must be equal to a multiplied by x minus 2 multiplied by x plus 3 and also plus b multiplied by x plus 1 times x plus 3 plus c multiplied by x plus 1 times x minus 2. Now, if we expand the right hand side, expanding the right hand side is going to give us this expression. So if we expand the right hand side, there is also another way on how you can handle this if you want, or you can expand the right hand side. But if you expand the right hand side, which if you can check, I've given you two methods. I gave two methods in this question, but as at now, what we are supposed to do now, because you are here, you are at this stage. Now the question is, I need to make one of them a 0. So when we look at this thing, so equating the numerators gives, so when we equate the numerators, what you're going to get is this. Now, the question is, instead, if you expand, it will somehow become tedious to complete the solution. So what you can do is this. The question is, I need just to remain with a situation where I have A, so that to help me to solve A. Also, I will need to equate so that I have a situation where I only have B, also where a situation where I only have a C. Now, how can we do this? So if I substitute in each, both from the left hand side and the right hand side, if I substitute where there is x and -1, let's substitute where there is x and -1, what will happen is this. If we substitute, if we let x equal to -1, then on the right hand side, what you are going to get is 2 multiplied by -1 squared minus 9 multiplied by -1 minus 35 is equal to A multiplied by -3, then multiplied by 2, because when I substitute where there is x and -1, I have a -3, I have a 2 here. Here, when I substitute where there is x and -1, I have a 0 and a 2. Again, I have a 0 and a -3. This means the B and the C, they all vanish. Reason being, how are they going to vanish? The reason being because they are multiplied to 0. Now, what I'm going to remain with is that on the left hand side, after simplifying, I'll have a -24. On the right hand side, after simplifying, I'm going to have a -6a. Now, -24 is equal to -6a. Solving, when you solve for a, we are going to get a is equal to 4. The next thing, since I've found A, I need then to find B. How can I find B? This means I can substitute. If you look at the expression on the page 13 in the example, the last one, from which this equation where we equated the numerators together, for me to get rid of A, I can substitute wherever there is x a 2. So when I substitute where there is x a 2, which means A and C, they will vanish. Because when I substitute where there is x a 2, what we are going to have on the left hand side is the 2 multiplied by the square of 2 minus 9 multiplied by 2 minus 35, which is equal to A times 0 times 5 plus B times 3 times 5, then plus C times 3 times 0. Then, when we simplify this expression, on the right hand side we are going to get a -45, on the left hand side we are going to get a 15b. Now, solving for b, we are going to have b is equal to -45 over 15, which will give us a -3. The next step we are supposed to take is we need to solve for c. To solve for c, it means we can substitute wherever there is x, we can substitute by -3 so that a and b can vanish. So that A and B can vanish. Now, to do so, if we substitute where there is x and -3, then what you're going to get is 2 times -3 times the square of -3 minus 9 times -3 minus 35, which is equal to A times -5 times 0 plus B times -2 times 0 plus C times -2 times -5. When we simplify this and evaluate, what you're going to get on the left hand side we have a 10, on the right hand side we have a 10c. Solving for c, we are going to get c is equal to 1. Therefore, we are saying this rational fraction in partial fraction form, as the sum of partial fraction is equal to 4 divided by x plus 1 minus 3 divided by x minus 2 plus 1 divided by x plus 1. So what we have done, we have expressed the given partial fraction, the given rational function, as a sum of partial fractions. Generally, if you can look at these partial fractions, their denominators are of degree 1. But the original expression, if you expand the denominator, you're going to find that the highest power will be 3. The next one is, we are going to solve the third question, number 8. We are going to look at it at your own time, since it's already solved, so you can look at it and then you see where we have challenges. You can contact me and we can go through it together. So now we are going to, again, if you look at example number 9, it's the same scenario, for which now if the only difference between example number 9 and the examples that you are from doing is this. In example number 9, the degree of the numerator is higher than the degree of the denominator. So in this case now, because the degree of the numerator is higher than the degree of the denominator, we can't convert this into partial fraction. The first thing that you need to do is we first need to divide. So by either long division or by synthetic division, when we divide x cubed minus 2x squared minus 4x minus 4 divided by x squared plus x minus 2, what we are going to get is the quotient to be x minus 3, then plus our remainder will be x minus 10. Which is divided by x squared plus x minus 2. When you reach this stage, if you look at this remainder divided by the divisor, here the numerator is of degree 1, the denominator is of degree 2. So the degree of the numerator is less than the degree of the denominator. So the only piece that we need to convert into partial fraction is this piece here, this one. So you need to convert x minus 10 over x squared plus x minus 2 into partial fractions. Now, if you look at the denominator, which is x squared plus x minus 2, you can express this as a product of linear factors. This expression can also be written as x plus 2 times x minus 1. Now, converting this x minus 10 divided by x plus 2 times x minus 1 into partial fractions, this you can also write it as equal to a over x plus 2 plus b over x minus 2. Similarly, just like the way we did in the previous example, algebraically adding these two, what you're going to get is ax minus 1 plus bx minus 2 times x minus 2 over x plus 2 times x minus 1. Now, for these two to be equal, it means the denominators must be, the numerators must be the same. So we are saying x minus 10 must be equal to ax minus 1 plus bx plus 2, which is this one. Now, here, I need to have a. I need to solve for a. To solve for a in shorthand form, I need to make b to vanish. B must vanish for me to solve for a. To make b vanish, it means I need to substitute where there is x in negative 2, because it's going to give me negative 2 plus 2, it will give me 0. 0 times b, the answer will be 0. So you have made b vanish. So now, if we substitute where there is x in negative 2, then we are going to have negative 2 minus 10 to give us a negative 12. Negative 2 minus 1 to give us a negative 3. Negative 3 times 3 to give us a negative 3. Negative 2 plus 2 to give us a 0. 0 times b to give us a 0. So what you're going to get is a negative 12 is equal to negative 3a. And so from this, negative 12 divided by negative 3 to give us a is equal to 4. Again, I go back to this equation that I obtained from the numerators after equating the numerators. Then if you look at this, since I've already found a, then I need to find b. So to find b, if you equate, how can I find b? I need to find b by equating x equal to positive 1. If I substitute where there's x a positive 1, my aim is to make a vanish. How can a vanish? How can a, in short, vanish means disappearing. How can I make a disappear? I can only do that by putting where there's, I'm in class. So by substituting where there is a positive 1, that means I'll make a vanish. So it will be 1 minus 1 to give us 0, but when I substitute where there is x, 1 here, to be 1 plus 2 to give us a 3. So generally, when you substitute where there is x, you substitute a 1, what you're going to get on the left hand side, you're going to have a -9, on the right hand side, we are going to have a 3b. So when we divide this, solving for b, we are going to have b is equal to -3. Hence, now what you're saying is the x minus 10 divided by x plus 2 times x minus 1 is equal to 4 divided by x plus 2 minus 3 divided by x minus 1 as a rational function, which is expressed in terms of the sum of rational functions, partial fractions. Now, the question is, after this, then, so if we go back to our original function, we say that the x cubed minus 2x squared minus 4x minus 4 divided by x squared plus x minus 2, this was equal to x minus 3 plus x minus 10 divided by x plus 2 times x minus 1. But then x minus 10 divided by x plus 2 multiplied by x minus 1, we replace it with 4 divided by x plus 2 minus 3 over x minus 1. So when we replace it there, then what we have done, we have expressed the rational function with the numerator greater than the denominator into partial fractions. Then the example is done. Okay. Now, in number 10, we are going to look at how we can convert a rational function with repeated denominator factors into partial fractions. The second piece is how we can convert rational functions with repeated factors, how we can express them into partial fractions. So we are saying, if we have a function f of x being a polynomial, then the partial fraction form of a rational expression f of x, which is divided by x plus a to the power n, with denominator containing n repeated factors, this one, we can write it as a1 divided by x plus a2 divided by x plus a squared plus a3 divided by the cube of x plus a plus ... plus an divided by the nth of x plus a. So basically, what I'm trying to say is this. For example, let's have a situation where this n is equal to 3. Let's have a situation where this n is equal to 3. Then what we are saying is f of x divided by x plus a to the power 3, you can write this in terms of partial fraction as a divided by x plus a plus b divided by the square of x plus a plus c divided by the cube of x plus a, in short. That's how we are supposed to write it. So now, these 3 dots means it's continue going. So if we have such a scenario, then from which we need to find the values of a, b, and c. This is now our main goal in this case. our main goal is to make sure that we find the values of A, B, and C. Let's look at an example. This first example, it's talking about a situation where you have this partial fraction. Now they are asking you to resolve it into partial fraction. So resolve 2x plus 3 divided by the square of x minus 2 into partial fractions. Resolve 3x plus 2 divided by the square of x minus 2 into partial fractions. Now, if you look at the denominator contains a repeated linear factor. We have a repeated linear factor. Now, how can we resolve this into partial fractions? How can we resolve this case into partial fractions? Okay, let me just beam this because yes, I've solved already this question which you're able to see on the board. So in this case, we are going to let 2x plus 3 over x minus 2 to the power 2 being equal to, the first step is you say a over x minus 2 plus b over the square of x minus 2. Now, from algebra, if you look at a divided by x minus 2 plus b divided by x, the square of x minus 2, from algebra, the common denominator between these two is the square of x minus 2. Now, x minus 2 into the square of x minus 2, you remain with x minus 2. So this x minus 2 times a to give us a times x minus 2. Then the square of x minus 2 into the square of x minus 2 to give us 1. So 1 times b to give us b. Now, for 2x plus 2 divided by the square of x minus 2 to be equivalent or equal to a times x minus 2 plus b over the square of x minus 2, because the denominators are the same, then we are going to equate the numerators. The numerators, which are 2x plus 3, must be equivalent to a times x minus 2 plus b. Now, to find b, to solve for b, I can make a vanish. Making a vanish means where there is x, I substitute a 2. When I make x equal to 2, then I'll have 7, because 2 times 2 is 4 plus 3 is 7. Then 2 minus 2 is 0, 0 times a plus b. This will give me b to be equal to 7. Then to solve a, now if you look at this, we are saying 2x plus 3 is equivalent to ax minus 2 plus b. When we expand this, the ax minus 2, what we are going to get is ax minus 2a plus b. Now, equating the coefficients, if we equate the coefficients, the coefficient of x on the left hand side is 2, the coefficient of x on the right hand side is a. So generally, a is equal to 2. Hence, when a is equal to 2, b is equal to 7, what we are going to have is 2x plus 3 over the square of x minus 2 is equal to 2 over x minus 2 plus 7 over the square of x minus 2. Now, I don't know if others are saying that they do not understand. Okay, let me just beam. I solve this question from the board. Let me just beam so that we can look at this question from the board. So I'll do this so that we can see what I'm talking about. Okay, now let's look at the situation which is on the board. Okay, so now So what we are having is okay, so let's look at this question from this point of view. Okay, now what we're having is 2x plus 3 divided by the square of x minus 1. So to partially, remember I mentioned to say if you have a rational function with repeated roots f of x divided by, for example, we can have x, let me just give another one, plus maybe a to the power, let me say 4, then this one in partial fraction form, this is equal to a divided by x plus 1, then plus b divided by the square of x, plus a, then plus a squared, then plus c divided by, plus c divided by x plus a cubed plus d divided by x plus a power 4. So you need, if the power is 4 of the denominator, which is repeated of the repeated denominator, then this partial fraction can be expressed as a sum of 4. This rational function can be expressed as a sum of 4 partial fractions. If it's 3, you are going to express it as a, now look at how the denominators are behaving. This is x to the power 4. The first one will always be a divided by x plus a to the power 1, of which it will just give us x plus a. The second one it will be the power 2, the third one the power 3, the fourth one the power 4. Now, in this case, let's now look at our example, which I've written on the board here. So, comparing this to what I outlined here, now the power of the denominator here is 2. So, the repeated factors, the highest power of this repeated factor is 2. So, now, this one, we can then write it as a divided by x minus 2 plus b divided by x minus the square of x minus 2. Now, let me maybe explain it like in the simplest form, like the way I explained the previous one. So, explaining it in the scenario where I explained the previous one, so what you can do, instead of you adding, we say using algebraic expression, adding the algebraic expressions on the right hand side, the other way we can do it is this. You would say multiply. Now, you look at the given expression, so we are going to say multiply each term on both sides, each term on both sides by this denominator of the rational function, given. So the denominator of this rational function given is the square of x minus 2. So you multiply each term on both sides by this. So now, when you multiply it, what you're going to get is this. So we are going to get x minus 2, the square of x minus 2 times 2x plus 3 over x minus 2 squared is equal to x minus 2, the square of x minus 2 times a divided by x minus 2, then plus again x minus the square of x minus 2 multiplied by b times the square of x minus 2. Now, when you reach at this stage, you see the square of x minus 2 and the square of x minus 2 will cancel. That means on the left-hand side of a equation, what you're going to get is 2x plus 3, which is equal to, now, on your right-hand side, this x minus 2, which is the denominator, will cancel with one of the x minus 2, so which you're going to remain with x minus 2 in the numerator. So then, in this term, the numerator you're going to have x minus 2 multiplied by a plus, now again, in the next term, the square of x minus 2 and the square of x minus 2 will cancel. We are going to remain with a b. Now, you are at this stage. The next step that you're supposed to take is let's just expand this so that we can equate coefficients. When we expand x minus 2 times a, what you're going to get on the left-hand side, it will be fixed. On the left-hand side, we have 2x plus 3 is equal to ax plus, minus 2a plus b. Now, when we reach this stage, so we can just say equating the coefficients. So when we equate the coefficients, so what you're going to get is when we equate the coefficients of these expressions, so when we equate the coefficients, which coefficients am I talking about? Is look at the coefficients of x, equating the coefficients from of x and the constant coefficients respectively. So what are we going to get then? So when we equate the coefficients of x together and the constant coefficients together respectively in that manner, so on the left hand side, you're able to see that the coefficient of x is 2. On the right hand side, the coefficient of x is a. So this means a is equal to 2. Again, on the left hand side, the constant coefficient is 3. On the right hand side, the constant coefficient is negative 2a plus b. Now, if this means b is equal to 3 plus 2a, but from the top, from the coefficient of x, we found that a is equal to 2. So this means you substitute where there is a in this equation, a 2. So what you're going to get is 3 plus 2 times 2, so which will give us a 7. So what you have found is that generally a is equal to 2, b is equal to 7. Now, after finding your values of a and b, then you substitute them. Our a is equal to 2, so this means the 2x plus 3 divided by x minus 2, the 2x plus 3, which is divided by the square of x minus 2, which we wrote as in partial fraction form a divided by x minus 2 plus b divided by the square of x minus 2, then we can substitute the values of a and b that we have found. The values of a and b, of which our a is equal to 2, our b is equal to a 7. Then what you have done, you have simplified your final answer. So what you have done, you have written the given the given rational function which has the denominator with repeated factors into partial fractions. Okay, so this is how we can resolve any given rational function with the denominator being in terms of repeated linear factors into partial fractions. So the next piece that we're going to look at is the last one. The next part that you're going to look at is the last one. So we are going to look at the last part, which involves again partial fractions. So okay, now let's look at partial fractions with quadratic factors. We are now going to look at partial fractions with quadratic factors. So let's look at partial fractions with quadratic factors. So we're now looking at partial fractions with quadratic factors. Now, we have a situation whereby quadratic factors, this is a scenario where if you look in the denominator, you have this expression that you can't factorize. You have this expression that you are unable to factorize. So now the issue here is, how can you handle such a situation? So you have this expression in the denominator that you can't factorize. In short, the type of factors that it has are non-real. They are complex in that scenario. So let's look at now. Let f be any polynomial. Then the partial fraction form of a rational expression, f of x, which is divided by ax squared plus bx plus c multiplied by x plus d, with a denominator containing a quadratic expression which does not factorize, without containing surds or imaginary terms. Remember, when you factorize this expression, you discover that the denominator contains surds or imaginary terms. So in short, in the denominator doesn't have real roots, in short. So if you have such a scenario, then the partial fraction form of this kind of a function is ax plus b divided by ax squared plus bx plus c, then plus c divided by x plus d. If we have a combination of a partial fraction with quadratic factors which are non-factorizable, and then in the denominator also there is this factor which is repeating, or it can even be non-repeating. So what we are going to get is f of x, which is divided by ax squared plus bx plus c, which is non-factorizable, then multiplied by x plus d to the power n. You can write this as, you can start by writing a1 x plus a2 divided by ax squared plus bx plus c plus a3 divided by x plus d plus a4 divided by x plus d cubed squared plus a5 divided by the cube of x plus d plus up to an divided by the nth of x plus d. So if this is the case, then we can look at one example. We can look at this example. Now this example, again, just like the way we did the first one, I think I'll just solve it by beaming. I'll just solve it by beaming to you. Basically, you already have the notes so that we can be fast. To make our work easier and fast, I can just beam the solving. So when I beam the solving, then we'll be able to see what is on the ground. Now let's look at this example. So I'll do this. I'll blind ourselves. So let's now solve the example which is given here. Okay. So we are looking at this example, into which they are asking us to express the given rational fraction, the given rational fraction 7x squared plus 5x plus 13, then divided by x squared plus 2 multiplied by x plus 1. Now, if you look at this rational fraction, the denominator, if you look at this rational fraction, the denominator is a combination. The denominator is a combination. This is a combination of a quadratic factor of a quadratic. This is a combination of a quadratic factor, which is x squared plus 2, and this quadratic factor is non-factorizable. So this quadratic factor is non-factorizable. Without introducing surds or the imaginary. Without you introducing the surds or imaginary. Now, and a linear factor, which is x plus 1. So because our rational function is a combination of a linear factor and a quadratic factor which is non-factorizable without the introduction of surds or other imaginary, this means this expression which you are seeing here, the expression which is 7x squared plus 5x plus 13, which is divided by x squared plus 2, then x plus 1, can also in partial fraction form is equal to a divided by the x squared plus 2, then plus b divided by the x plus 1. Oh, sorry. We are supposed to have, now if you look at this quadratic factor, because it's non-factorizable without you introducing the surds, this means under here we are going to have ax plus b, then plus c. Other texts you find they will write maybe a plus bx. Other texts they will write like this, but it's just the same thing, one and the same thing anyway. So now, after when you reach this stage, the next step that you're supposed to take is this. So you look at this function, you look at this equation that you have formed, where you have this rational function which you have equated to being the sum of two partial fractions. Now what you're supposed to do next is this. You can either add the right hand side. After you do the addition, then you equate the numerators, or you can do it in the way that I'm doing it on the board. So what you can do is multiply. So the next step you're supposed to do is you multiply both sides, or rather each term, by multiply both sides by the denominator x squared plus 2 x plus 1. So that is what you are saying is, if I multiply the left hand side by x plus 2 times x plus 1, this will cancel with the denominator. So what I'm going to get, we are just going to have the numerator 7x squared plus 5x plus 13. So when you multiply both sides by x squared plus 2 times x plus 1, what you're going to get is, on the left hand side, we have 7x squared plus 5x plus 13. On the right hand side, if we multiply ax plus b divided by x squared plus 2, if we multiply it by x squared plus 2 times x plus 1, so the x squared plus 2 will cancel the denominator. We are going to remain with x plus 1 times ax plus b, plus, if we multiply c divided by x plus 1, we multiply it by this denominator, what you're going to get is the x squared plus 2 multiplied by c. So now we are going to solve this question using, from the coefficient point of view, where we are going to equate the constant coefficients, the coefficient of x squared and also the coefficient of x. Now to do so, what we need to do is we need to expand the right hand side of our equation. So what we are having is 7x squared plus 5x plus 13, which will give us, if we multiply x plus 1 times ax plus b, what we are going to get is x squared plus a plus bx plus b. Okay, so this is what we are going to get. Then plus cx squared plus 2c. So simplifying the right hand side, what we are going to get is a c plus 1 multiplied by x squared plus a plus b multiplied by x, then plus b plus 2c. So what we have done is, now we have decided to write this expression. We have simplified it, we have expanded, then we have simplified. Now, looking at, for the right hand side to be identical to the left hand side, the only possibility is that the coefficient of x squared on the right hand side must be equal to the coefficient of x squared on the left hand side. Now on the right hand side, the coefficient of x squared is c plus 1. On the left hand side, the coefficient of x squared is 7. Next, again, the coefficient of x on the right hand side is a plus b. The coefficient of x on the left hand side is 5. The constant coefficient on the right hand side is b plus 2c, and the constant coefficient on the left hand side is 13. Then, now, from C plus 1 equal to 7, this means our C is equal to 6. From A plus, now, before we find A, we need to get B from the constant coefficients which are equated together. So, then from B plus 2C, which is equal to 13, now you see, we want to get B. Here we can find that our B is equal to 13 minus 2C, from which we are going to get that 13 minus 2, our C is 6, so then which will give us 1, because 2 times 6 is 12, so we are going to have 13 minus 12, which will give us a 1. Now, again, from A plus B equal to 5, what we have is A is equal to 5 minus 1, but then, minus B. So our B is equal to 1, so we are going to have A is equal to 5 minus 1, which is going to give us A is equal to 4. So now we have found our C being equal to 6, our B being equal to 1, and A being equal to 4. Then our partial fraction, which in partial fraction form, the rational function 7x squared plus 5x plus 13, which is divided by x squared plus 2 times x plus 1, which is equal to, remember, we wrote it as ax plus b over x squared plus 2 plus c over x plus 1. We substitute a, we substitute 4 here. So this means our rational function given into partial fraction, we are going to get the expression in the form our a is 4, x plus our b is 1, plus our c, which is equal to 6. 6. So we have expressed this rational function, which has a denominator, this rational function which has the denominator with a quadratic factor that cannot be factorized into real factors. Or rather, that cannot be factorized without the use of surds and also imaginary numbers. So this is how we can handle such a question. Now, the next thing that you are supposed to look at, so there are a lot of examples concerning such kind of questions. So in the notes that I've sent on Moodle, you can go through the notes. There are a lot of examples that I've put that you're going to be using most of the times. You can just go through them. Those other examples that I've made that I've not explained, but of which they are explained in the notes. The explanation is straightforward. So you're going to look at them, and then if you have challenges, then still we can discuss them on other platforms. Okay. So the next thing so this is the expression that we are given. So, and then after solving, now we also have another question which they're asking us: resolve 3 plus 6x plus 4x squared minus 2x cubed over x cubed squared times x squared plus 3 into partial fractions, of which please find time to go through the answers find time, please, to go through them. Then you're going to see that the final solutions will be not that challenging. Okay, so the final answers are here. So generally, we look at some applications that involve partial fractions. So resolving an algebraic expression into partial fractions, basically, it's used in integration. When you come next semester, as you'll be learning next semester, you're going to do integration. So you'll be looking at functions, you'll be integrating functions that need to be transformed into partial fractions. That's when you can now do the straightforward integration. The other part is same partial fractions are used in determining inverse Laplace transforms in calculus and advanced calculus. So you'll be having all these scenarios as you'll be solving most of the time. So whereas you start doing calculus, you'll be using the partial fraction. There's a part where they ask you to use partial fraction. They will not really ask you things to do with partial fractions, but they will ask you a question that they want you to integrate, but then in the process of integration, for you to handle it, you need to use partial fractions. So this is the end of this lecture. Thank you so much for listening. The next session of your class, it will be done by Mr. Moyo. He's the one who will take you from trigonometry, complex numbers, and matrices. So he's the one who's going to take up from me. So all contacts are diverged to Mr. Moyo. Thank you so much for your time and attention. This is the end of the session.